Welcome to the deep dive. We dig through the research, pull out the key facts, and we'll get you up to speed on one important topic. Today, we're diving into something absolutely essential for life, especially for our food: nitrogen. Standard farming. It often leans really heavily on adding external synthetic nitrogen. But what if the farm itself could be part of the nitrogen solution?
That's exactly what we're looking at with agroforestry systems. Now, if that term's new to you, it basically means integrating trees deliberately with crops and sometimes animals too. And it's not just a different way to farm. These systems offer, well, a whole host of benefits. Things like better crop production, less soil erosion, more biodiversity, and they even help with climate change mitigation.
Right. So for this deep dive, we've looked at a really thorough review. It covers global data from, 1950 right up to 2021.
That's the one.
And our goal here is to give you a clear picture of how nitrogen, this absolutely critical element, actually moves through these agroforestry systems. We'll look at, how it gets in, how it cycles around inside, where it gets stored, how it might get lost, and ultimately what it all means for yields and efficiency. It's quite a journey.
Okay, so let's start that journey with N inputs. Where does the nitrogen actually come from? Now, like you said, conventional farming often means lots of synthetic fertilizer. Agroforestry is, well, it is different. You still have traditional inputs sometimes like manure or compost, maybe some inorganic fertilizers. Globally, that adds up to about 36 kilograms of nitrogen per hectare per year on average in these systems. But there's something else, something really central to agroforestry.
And what's the main player there, the really distinguishing thing for nitrogen input?
Oh, it's definitely N2 fixation, biological nitrogen fixation. You have these leguminous trees, think beans, peas, that family in the system. They have this amazing symbiotic relationship with bacteria in their roots. And these bacteria, they can take nitrogen gas, N2, straight from the atmosphere.
Which plants normally can't use, right?
Exactly. They can't use N2 directly. But these bacteria convert it into a usable form, like ammonia. And this is a huge input. Globally, the average is around 240 kilograms of nitrogen per hectare per year, just from this process in agroforestry.
Wow, 240 kilos.
Yeah. And in some specific systems, like what they call improved fallows, it can be way higher. We're talking 300, maybe even up to 650 kilos per hectare per year. It's really impressive.
So this basically means the farm is generating a big chunk of its own fertilizer, reduces the need for buying the synthetic stuff?
Precisely. It's a fundamental shift. Less reliance on those external, often fossil fuel-intensive inputs.
That's huge for sustainability. Are there things that affect how well these trees fix nitrogen? Like what makes them better or worse at it?
Yeah, absolutely. Several factors. For instance, having enough phosphorus in the soil often helps boost N2 fixation. And those mycorrhizal fungi in the soil, those networks that connect plant roots, they seem to play a role too, interacting with the bacteria.
Interesting.
But conversely, if you dump a lot of nitrogen fertilizer onto the field anyway, the trees might actually dial back on fixation. It's like, why bother making it if it's already there,
Okay, that makes sense. So besides this amazing natural nitrogen factory, you mentioned traditional inputs are still used sometimes, but it varies a lot depending on the type of agroforestry.
It really does vary. You look at something like home gardens, maybe they get around 31 kilos per hectare per year. But then intercropping systems, where crops are grown between trees, that can be much higher, almost 92 kilos. Shaded systems, like coffee grown under trees, maybe around 36 kilos. And then silvopasture, trees with animals grazing, often quite low, maybe 7 kilos.
And some systems barely get any external nitrogen at all.
That's right. Things like those improved fallows we mentioned, or riparian buffers, tree strips along waterways, they often get zero external N. They rely pretty much entirely on fixation and internal cycling.
Now, we shouldn't forget the stuff just falling from the sky. Atmospheric deposition, I gather that's another piece of the puzzle, even if it's hard to measure sometimes.
Indeed. You get nitrogen compounds from the atmosphere, gases, dust, rain landing on the land. We don't have perfect numbers specifically for agroforestry deposition everywhere, but the general global average has been increasing. It was about 1.8 kilos per hectare per year back in 2016, which was 8% up from the 80s. So it's definitely a contributor, and these systems with their vegetation are likely capturing a fair bit of it. It's just often not accounted for in the budgets.
Okay, so nitrogen arrives via fixation, some traditional inputs, and deposition. Now, let's follow it inside the system. This internal cycling, you said, is where agroforestry really shines in terms of efficiency.
Exactly. A really central process here is N-mineralization. It's basically decomposition. All this organic matter, dead leaves from the trees, fallen branches, old roots, those nitrogen-rich nodules from the fixing trees, plus crop residues, animal manures if they're animals. As all that breaks down in the soil, microbes release the nitrogen back into inorganic forms, mainly ammonium and nitrate. And those are the forms that plants can readily take up.
So it's like nature's recycling program right there in the soil. How do the rates compare to, say, a standard farm field?
It varies. Some studies, like some in India looking at agri-silvicultural systems, found mineralization and nitrification rates were higher, maybe 12 to 37% higher than nearby conventional fields. Others find the rates are pretty similar. It seems to depend a lot on the specific conditions. Temperature definitely plays a role. Warmer soils generally mean faster mineralization. Soil moisture effects are a bit more complex, can go either way depending on the situation.
And then you mentioned fixed nitrogen transfer. So the nitrogen the trees fix doesn't just stay with the tree, it gets shared.
Yeah, that's another fascinating part. The nitrogen fixed by those leguminous trees can actually be transferred over to the crops growing nearby.
How does that happen?
Well, there seem to be three main ways. One is just through the decomposition of tree litter and roots, releasing N into the soil where crop roots can get it. Another is that trees can release nitrogen compounds directly from their roots, root exudates. And the third way, which is really cool, is through those common mycorrhizal networks. The fungal threads can actually connect the roots of the tree and the crop, potentially moving nitrogen between them.
Wow, like an underground trading network?
Sort of. There was a study in Canada in the shelter belt system. They found up to 40% of the nitrogen in the crops actually came from the nearby leguminous shrubs. The closer the crop was to the shrub, the more nitrogen it got.
40%. That's incredible.
That's a huge benefit.
Okay, and then there's this idea of trees as deep-rooted miners almost, pulling up nitrogen from way down below. Tell us about that, the end pumping from subsoils.
Right. This is really important. In many conventional farming systems, nitrogen that leaches down below the crop root zone into the subsoil is effectively lost to the current crop. And quite a lot can accumulate down there, sometimes, 70 to over 300 kilos per hectare.
Just sitting there, unused?
Pretty much. But trees in agroforestry, especially deep-rooted ones, can send their roots way down into those layers. They absorb that nitrogen, effectively pumping it back up into the tree's biomass. Then, when the tree drops leaves or its fine roots turn over near the surface, that nitrogen gets released back into the topsoil where the crops can reach it.
So they're rescuing lost nutrients.
Exactly. It's a fantastic recycling mechanism. There was an example from Quebec where hybrid poplar trees reduced the amount of nitrate leaching out of the subsoil by 30 to almost 230 kilograms of N per hectare per year. That's nitrogen that would otherwise potentially pollute groundwater.
That really highlights a potential loss in other systems we might not even think about.
It does.
And trees do one more trick, right? Cleaning the air. Ammonia capture.
Yes, another benefit. Trees are quite good at capturing ammonia gas, NH3, and other nitrogen pollutants directly from the air onto their leaves and bark. Research has shown tree strips, say planted near animal housing, can capture up to 27% of the ammonia being emitted. In silvopastoral systems, it could be as high as 60%.
So it reduces air pollution.
Right, which is good in itself. But then that captured nitrogen often gets washed off the leaves by rain down into the soil below the tree. So it's another way nitrogen gets added back into the system's cycle, enhancing fertility.
Okay, so the internal cycling is incredibly dynamic. What about storage? Where does nitrogen end up long-term in these systems? Sequestration, right?
Correct. Agroforestry systems are really good at storing nitrogen, acting as long-term sinks. This happens in two main places, the plant biomass itself and the soil.
So in the trees and plants.
Yeah, in the wood, leaves, roots. The amount stored in biomass varies, of course, but estimates suggest maybe around 36 to 43 kilograms of nitrogen per hectare per year is locked up in total plant biomass. Interestingly, a bigger chunk of that, maybe 24 to 28 kilos, seems to be in the below-ground biomass, the roots.
But the soil is the really big bank for nitrogen.
It really is. Most of the nitrogen in soil isn't just floating around. It's incorporated into soil organic matter, often protected inside soil aggregates. And agroforestry can really build up soil organic matter. The numbers are quite striking. In humid tropical areas, soil nitrogen stocks under agroforestry can be, get this, 46% higher than under standard crop monocultures.
46%?
Yeah, and even in sub-Saharan Africa, it's around 20% higher. Yeah. The estimated rate of N sequestration just in the soil component is thought to be around 98 to 154 kilograms per hectare per year. That's roughly 3 times more than what's stored annually in the biomass.
That's massive. And storing nitrogen in the soil helps with other things too, right? Like carbon.
Absolutely. Building soil organic nitrogen is tightly linked to building soil carbon, so it's a win for climate change mitigation too. Plus, stable organic nitrogen is less likely to be lost as polluting gases.
Okay, this sounds overwhelmingly positive, but we need a balanced picture. What about nitrogen losses from agroforestry systems? Are they always lower?
Generally, yes. Losses through erosion, runoff, and leaching tend to be significantly lower. The trees and permanent ground cover act as physical barriers. They slow down rainwater runoff, giving it more time to soak in. In fact, infiltration rates can be like 75% higher than in monocropping.
So less water running off the surface, taking soil and nutrients with it.
Exactly. The vegetation protects the soil surface from raindrop impact. Tree roots help bind soil together, improving its structure, and the trees reduce wind speed, cutting down on wind erosion.
And that nutrient pump effect we talked about, the deep roots pulling nitrogen up, that would also reduce leaching losses deep down.
It certainly contributes. Put it all together, and the data suggests agroforestry can cut overall N loss from leaching, runoff, and erosion by something like 55 to 60% compared to monocropping. Soil erosion itself reduced by half, runoff down by over half as well.
That's a huge reduction in potential pollution. But what about gaseous losses? Things like nitrous oxide, N2O, that's a potent greenhouse gas.
Right, N2O is a big concern. It's mainly produced by microbes in the soil through processes called nitrification and denitrification. The global average estimate for N2O emissions from agroforestry systems is around 4.7 kilograms of nitrogen per hectare per year. But, and this is important, it's a very nuanced picture.
Nuanced how? Because I think I saw that some agroforestry systems can actually have higher N2O emissions than conventional fields. That seems counterintuitive.
It does, but it happens. It really depends on the specific system and how it's managed. Systems that have a very high nitrogen input, especially from those very active N-fixing trees or from adding lots of residues back to the soil, can sometimes create conditions ripe for N2O production. So things like those improved fallows or some shaded perennial systems have actually shown higher N2O emissions in some studies, sometimes substantially higher, like over 100 or even 500% higher than comparable conventional fields.
Wow. Okay, so more nitrogen input can sometimes mean more N2O loss.
It can if the conditions are right. Things like soil moisture, temperature, oxygen levels all play a role. However, other types of agroforestry consistently show lower emissions. Shelter belts, for example, were found to be 74% lower. Riparian buffers, 75% lower.
Why lower in those cases?
It could be lower overall N inputs in those particular systems. Or maybe the trees influence soil conditions in a way that promotes more complete denitrification, turning nitrogen compounds all the way back to harmless N2 gas instead of stopping at N2O.
So the key takeaway isn't simple. It's not agroforestry good, conventional bad for N2O.
Not entirely, no. It's much more about the specific design and management. How much nitrogen is going in, what are the soil conditions, what type of system is it? These details really matter for managing potential trade-offs like N2O emissions.
That's a really critical point. And briefly, what about the other gas, nitric oxide, NO?
Nitric oxide, NO, is involved in atmospheric chemistry, ozone formation, acid rain. There's less research on NO emissions from agroforestry specifically. Generally, the studies that exist suggest NO emissions are often similar to conventional croplands. Although, again, some intercropping systems have shown lower emissions, typically quite small amounts, like 0.1 to maybe 0.6 kilos of N per hectare per year.
Okay, so let's bring this all back to the farm level. We've seen how nitrogen comes in, cycles, gets stored, gets lost. What does this mean for the actual output? The crops, the efficiency, nitrogen use efficiency, or NUE?
Right, the payoff. And generally, the payoff looks pretty good. The most consistent finding is that agroforestry often leads to increased crop yields. We mentioned maize in sub-Saharan Africa earlier, yields increasing by 700 to 2,500 kilos per hectare. That's an 89% to over 300% increase in some cases.
Huge increases. And why is that? Is it just the extra nitrogen?
The improved nitrogen availability from fixation, from that subsoil pumping, from reduced losses, is definitely a big part of it. But it's also other things the trees do. They can improve water availability for crops, buffer extreme temperatures, creating a better microclimate, and generally improve soil physical properties. It's a whole package of benefits.
Though it's fair to say, if the trees aren't managed well pruned properly, they could compete too much for light or water and reduce yields in some cases.
That's true. Management is key. But it's not just about the quantity of the yield. Agroforestry can also improve the quality. We see increased nitrogen content in the crops themselves. That maize example again in content was almost 3 times higher in an alley cropping system compared to just growing maize alone.
So more nutritious food or feed.
Exactly. Which means higher nitrogen output leaving the farm in the harvested product. And of course, if you're harvesting timber from the trees, the nitrogen in that wood is another significant output.
Which brings us to overall nitrogen use efficiency, NUE. How efficiently are these systems using the nitrogen available to them?
NUE is basically a measure of how much of the available nitrogen actually ends up in the harvested products versus being lost. And the research points pretty clearly to agroforestry systems generally having higher NUE than conventional agriculture.
Higher efficiency.
Yes. For example, one study in Germany calculated NUE at 0.91 for an agroforestry system compared to somewhere between 0.64 and 0.87 for typical conventional farming there. And this higher efficiency comes from that combination we've been discussing. You get more nitrogen output in the harvest, yields and timber, and you have lower nitrogen losses along the way.
And higher NUE is good for the farmer's bottom line and the environment.
Absolutely. Better crop growth, less wasted nutrient, less pollution, fewer greenhouse gas emissions per unit of product. It's really central to sustainability.
So we've painted a really detailed picture, but as we wrap up, it feels like there are still pieces missing. What are the big uncertainties? Where do we need more research?
Oh, definitely. Despite everything we know, there are significant gaps. We really need more direct, on-the-ground measurements of some specific processes. Like, how much nitrogen are tree roots really releasing through exudates? How much are those deep roots actually taking up from specific depths? What are the exact pathways and amounts of nitrogen loss under different climate conditions or management styles? We need more quantitative data.
And how does climate change throw a wrench in all this?
That's a huge question.
Mm-hmm.
Warming temperatures, changes in rainfall patterns, more droughts, more intense storms, all these things can potentially destabilize these nitrogen cycles. Warmer soils might speed up mineralization, maybe leading to more losses if plants can't take it up fast enough. Drought could stress the end-fixing trees, reducing their capacity. Extreme rain could increase runoff and leaching, even with trees present. N2O emissions are also sensitive to moisture and temperature, so understanding how these systems will respond to climate change and finding ways to make them even more resilient has to be a major focus for future research.
Okay, so let's try to summarize the big picture then. Agroforestry, while complex, seems to fundamentally reshape nitrogen dynamics in a positive way. You get enhanced inputs, especially that biological N2 fixation.
Yeah.
You get really efficient internal cycling decomposition, that amazing deep root pumping, even cleaning ammonia from the air. Then there's significant long-term storage in biomass and especially the soil, and generally lower losses through erosion, runoff, and leaching. Although the picture for gaseous losses like N2O is more complex and depends on the system.
Right.
And the result is often higher output, better yields, more nitrogen in the crops, plus timber leading to overall greater nitrogen use efficiency.
That sums it pretty well. It's a system that tends to work with natural nitrogen processes rather than solely relying on external additions and potentially overriding those cycles.
Which leads to a final thought for you, our listener, to ponder.
Consider this. If managing nitrogen better is so absolutely critical for feeding the world sustainably, and agroforestry offers such clear advantages in how nitrogen is used and conserved, what needs to change at a bigger scale? What kind of global policies could really help unlock the potential of these systems, especially for smallholder farmers around the world, to boost food security and build environmental resilience? Something to think about.